Now let's get started on chapter 5. It is on eigenvalues and eigenvectors. We'll be doing 5.1 and 5.2 in this chapter. This is an important topic of study. You'll probably see later in your career in engineering and mathematics. All right, so first the definition, 5.1. Eigenvalues and eigenvectors. And go ahead and write that down. Let A be an n by n matrix. Let lambda be in the reals. That's the lowercase Greek letter lambda. So lambda is called an eigenvalue of A if there exists a vector x, non-zero, such that ax equal to lambda. So then the vector x is called an eigenvector corresponding to lambda. It's also called a characteristic value or characteristic vector. Little note here, lambda could be complex or imaginary in the complex plane, but we are going to restrict it to real numbers in chapter 5. We may go on to see that in chapter 9. I haven't actually decided yet the path we're going to take at this point, given our online situation. However, let's continue. So one of the concepts of it is, and I'm not going to get into applications and details of that right now, maybe a little later. We want to be able to do the calculation and then talk more about it later. So if you have some vector x like that, then lambda is basically scaling x. So it could be negative, point it the other direction, or it could make it go shorter or longer. So it's a scale of x. So the equation then is the matrix equation ax equal to lambda x. And our goal will be to find the eigenvalues and eigenvectors given a matrix. All right, so let's take a look at this. So first, let's look at an example. Oops, let's change that color. Okay, so let's first just verify if A is equal to the matrix 2, 0, 0, negative 1. And I'm just picking something real simple to show you that's a diagonal matrix, but it doesn't have to be, of course. And lambda 1. So you're going to get different values of lambdas. You're going to find there'll be multiple lambdas to look for. So if lambda 1 is equal to 2 and x1, so that means they're corresponding, equals to 1, 0. Basically, you want to show that the matrix equation works. So we want to show that ax1 is equal to lambda 1 x1. So we're just verifying that product right now. So let's take a look at that. So you have the matrix 2, 0, 0, negative 1 times the vector, which is 1, 0, like that. And what we'll do, let's go ahead and multiply that out. And then we'll look at and see what lambda x1 would be. And again, this is a pretty simple case, but so you have 2 by 2, and this is a 2 by 1. Insides match, so the resulting will be a 2 by 1. So do this by hand. So 2 times 1 is 2, plus 0 is 0, so this is a 2. And then 0 times 1 is 0 and 0, so you get a 0. We add that all up. So you get 2, 0. And if you look at what was lambda, lambda was 2. So 2 times x, which is 1, 0, equals 2, 0, which is, of course, your x1. Okay, so that works. So that's the concept. That's what we're talking about. So you do a product of a matrix and a vector equal to a scalar times the vector. Okay, so try x2 on your own, and it should work out just fine. Okay, I'll probably write that up later, but go ahead and try that. Okay, so now let's talk about finding eigenvalues and eigenvectors. That's really what we want to be able to do in this section. And focus on doing this all by hand. You can use your calculators and whatever to kind of help simplify things and verify, but you got to be able to do this stuff by hand. All right, so finding, and I'm going to abbreviate, right? It makes it easier. So eigenvalues and eigenvectors. So this is the setup that you do, and it's slightly different than what the book will have. And I'll tell you where to find that. They switch the order, but you'll see, I'll point it out as I go here. Page 291, they talk about switching how you bring the values to whatever side. Okay, I'll get to that in a second. So you have AX equal to lambda x. Then what you do is we can basically bring or subtract the entire side either way. We can bring all of the lambda x to the left-hand side or vice versa. So either way, it doesn't matter. So what you do is you form this equivalency. And I'm going to stick with what I have in the notes. You can look at the book and see how they're different. So bring everything to the left-hand side, AX to the right-hand side. So these are symmetric property, right, of equality, so you can bring it to either side. So what you write, lambda I x, you multiply by 1, equal to AX. Then bring the AX to the left-hand side, and so you get lambda I x minus AX equal to the 0 vector. Then we factor out the vector x. And you won't have to do this each time. I'm kind of deriving it a little bit. So it's lambda I minus A x. And that is equal to the 0 vector. All right, so you end up getting this system of equations that you solve. Okay, so that's, I said that wrong. You end up getting that matrix, and you can solve that. I'll show you what I mean. Because lambda is the variable. So basically, this system has a non-trivial solution if and only if lambda I minus A is not invertible, And that is true if and only if the determinant, so that now that's a matrix, so it's not invertible, right? So basically, just to clarify, maybe a little bit, we have the matrix equation Bx equal to 0. So that has a non-trivial solution if B is not invertible, right? Because if B was invertible, then you only get the trivial solution because that's a homogeneous system. Okay, so sit on that for a second. So what we want then is the determinant to equal 0. So you got to picture this as a matrix. So that has to be not invertible, and that's true if and only if lambda I minus A is equal to 0. So that's what you solve. Okay, so this is more or less the, so that's the definition of eigenvalues and eigenvectors. And then this is kind of the property of what you do. Okay. So call this a theorem. So let A be an n by n matrix, then 1, an eigenvalue of A is a scalar lambda, and I'll say in R, such that the determinant of lambda I minus A is equal to 0. And then 2, the eigenvector of A corresponding to lambda are the solutions of that system we just derived. Are the solutions to the system lambda I minus A x equal to the 0 vector. So one thing to point out is, going back here, what you could do is you could bring all of this to the right-hand side. So another way to write this is, or define it, is A minus lambda I x equal to 0. Both will work, but I'm going to stick with what I have in my notes, which is this form here. And you can do what the book does, or either way is fine. It'll both work out. Okay, a couple more details of this. The equation of the determinant of lambda I minus A equal to 0 is called the characteristic equation of A. So it's called the characteristic equation of A. So when you do that, you'll see, it'll be much more clear once we do an example. So it's lambda I minus A determinant. What you will get is a polynomial. You'll get lambda to the n plus Cn minus 1 lambda to the n minus 1, etc., down to C1 lambda 1, or lambda, sorry, plus C naught. That's called the characteristic polynomial. It's called the characteristic polynomial. So then you set that equal to 0. And finding the roots of that polynomial, so the roots of this, zeros, right, are the eigenvalues. So that gives the eigenvalues. Okay, so that's what we will do for an example. Okay, so let's do an outline of how to set this up, and then we'll do an example. Okay, so here's the outline.